Okay, so in this video clip we're going to take a look at some C++ code for implementing Hull and White 2004 employee stock option model. And this is again a binomial lattice type construction, and C++ tends to be quite computationally efficient, but works better if the code has been optimized. So a static implementation of binomial tends to be less efficient than a more optimized type construction, just to see the extent to which we can improve on the static implementation of Hull and White. We have here in this snippet of code a timer here, and we can look at the starting time and the end time and consider evaluate this code in terms of efficiency and then also in terms of accuracy. Again, it's just a standard implementation of Hull and White, and efficiency is one issue, but also accuracy. So let's just see how we might implement that. So we can just basically copy the code and then directly input. And for simplicity here, I'm just going to put this into an online GBD compiler. So the online compiler, online GBD, is can be accessed in any Chrome browser or internet browser, and we have to pay attention here once we get on that it's a C++ compiler. So I'm going to start afresh here. Okay, so onlinegbd.com, and then select, so again this is empty basically, and we need to designate a language, so C++, and I'll remove whatever content is there and just do a direct paste. And again, we have here is we have these parameter inputs. So the spot price is 100, K is 100, vesting period is 2 years, 10 years maturity for the option, 20% volatility, stock price volatility, no dividend, 4% exit rate, 1.5 multiple, and 6% risk-free interest rate with n equal to 100. Now we could raise that to 500. And let's run, and we can have a look at our output, and we get 28, 40, 26, and it took 0.039 CPU seconds. Okay, so let's compare that then to the original paper. The paper is available on SSRN, so Accounting for Employee Stock Options, Accelerating Convergence, and we'll just go to where we have some output here, a table that constructs that we have true value, and then we look at 500 step, and you can see here with a 500 step with the same parameter values, you can verify the parameter values here. It's 28, 40, 26. Go back to the online compiler, and we have 28, 40, 26. Okay, so that looks reasonably okay. And let's go to set up another instance then, the more efficient code. So online GBD, and this opens up a new instance. Again, we'll select the language, C++. We remove the content, and to get the more efficient C++, the more optimized C++ code with a specification for boil low, which makes the code oscillate less, makes the output more accurate, and with a lower number of steps produce output that is more consistent with true. Let's just copy that directly into the online GB compiler, and we paste, And then this code is also consistent with the FASB guidance. Okay, let's run that now. A quick check before we run. Let's examine the parameter inputs. They're the same as before. We'll raise to 500, but the parameter inputs are the same as before. And okay, let's just run and see what result we obtain. And again, it's 004417, but we have a value here of 2786. Let's compare with what we have here. 2786.75. 2786.75, okay, is what we obtain. And the amount of time 004417 seconds with the dynamic code, but with the static code it was 039319. Okay, so we can see that the this code, the second snippet of code in the portal, right, the C++ code with refinements based on insights developed by Boileau, 1994. This code is faster, but it's also more accurate. It's closer to true. So what is true? The true value here is 2785.51, and that's a value that was provided to us by Civentic Wiener Zapatero. 2008. Svi Wiener sent us these true values when we gave him the different parameter values that we were considering for the paper. So we know that this is true, and we know that the output that we get, we know that the value that we obtain in terms of the code 2786 is close to true, and that's for the hull white Boileau specification. Okay, so next thing then is let's raise this to 5000. Right, let's go back to our parameter inputs and just put in for 5000, and we'll run. And again, we should get higher level of accuracy, but it'll take a bit longer. Okay, and we'll do the same here with the more efficient code. And the nice thing about the online GBD compiler is you can run both simultaneously, and it's not a drain in your resources. Right? It's not a drain on your computer resources. So let's run this, and let's go back. Now, did we compile here in the first snippet? Did we? Yeah, okay. 280345, and it took 4 seconds. So let's compare that. This is 5000 steps. 5000 steps. Let's go back to the paper. Okay, with 5000 steps, 280345, 280345 took 4 seconds. Let's have a look at the more efficient code, 278535. It's 053 CPU seconds, so a lot faster, but the result is more accurate, 278535. Let's go back to the paper at 5000 steps, 278535. So it's more accurate when we compare it to true, but it's also just took half a second in terms of estimation time. So it's a lot more efficient than the full 4 seconds it took to complete here when we compare it to the static code. Okay, so that's a comparison of the two snippets of code, and it's clear when we look at the implementation here that the first snippet of code, while it does the job, it tends to be less accurate, and we can optimize that code and generate higher efficiencies using C++ when we make better use of dynamic memory. And of course the Boileau specification as well improves accuracy as well, and that's Boileau is typically applied for options with barriers in where we're using lattice type approach. Okay,